Alright guys, once again my name is Dr. Tshabalala. Welcome to our lesson today of work, energy and power. It's very interesting. You'll realize that actually we've been doing work, energy and power since from grade 10 when you decided to take physical sciences as one of your subjects. Now our content today is going to be very easy and very interesting as well. I'm going to take this opportunity to explain some definitions. We're going to do a definition of work, what is work, from work, energy and power point of view. We are also going to define force, we are also going to define power. And thereafter we're going to take a look at something that is very interesting, types of energies. Please note, energies are not limited only to these three types. But according to our scope of work, we're going to do only these three types of energy, which are potential energy, kinetic energy, mechanical energy, and thereafter we're going to do some principles and theorems. And it's very important that you understand these principles and theorems for our calculations. The first principle that we're going to do is the principle of conservation of mechanical energy, which is very important. And thereafter we're going to do what we call work energy theorem. Now let's start with our work. Now, in the preceding video of vertical projectile motion, we also dealt with force. And there we treated the force as a vector. Even here, force is a vector. And you'll see that the vector, a force being a vector, plays a very important role here. Now, force, we are saying force is a push or a pull. Force is a push or a pull. So you are applying a force to something if you are causing that particular thing to be pushed in a certain direction. But under this topic, we're going to deal with what we call the resultant force. The resultant force, according to Newton 2, is normally denoted by force is equals to MA. Now, this is the net force. Let me explain this. The net force is different from the normal force. Any other normal force. The net force is different from any other normal force. Let me make a typical example. There might be 5 forces. I'll make a typical example with this. There might be 5 forces acting on this. I'll make an experiment right now. There are 2 forces acting on this right now. I'm applying a force on this side. I'm also applying a force on this side. Now the net force will be the force that will cause this thing to accelerate. If this thing is accelerating this way, then the force that caused the acceleration is certainly not this force, although it was applied. This is just any other force which was applied here. But the force that causes an object to accelerate is the net force, the total force that is acting on an object, and is normally called the net force. There might be several forces acting on an object, but the force that causes acceleration is called the net force. Say 2, I see a question?
The acceleration means when an object moves to another what?
Acceleration occurs when you change velocity.
Okay.
Yeah, when you change velocity, if your velocity was 0 meters per second, now all of a sudden you are changing to 1 meters per second. Or if your velocity was 1 meters per second, all of a sudden you are changing to 2 meters per second. That is acceleration. Do you guys understand the angle of the resultant force? You need to be able to understand that and explain it to anyone else. The resultant force is the one that is causing the acceleration of an object, not any other force that is acting. There might be several forces acting on an object, but the force that causes the object to accelerate is called the net force. Now let's move forward. Now let me again indicate here. I'll do a little bit of grade 10 mathematics. It's very important that you apply it here. I normally say that mathematics is a queen of all sciences. So you cannot do sciences adequately without proper background of mathematics. Now you will see, we are going to apply grade 10 mathematics. Now, suppose I'm applying a force in this way. I'm applying a force, I'm telling you that I'm applying my force in this way. So this is my force. I'm applying it in this way. And I'm telling you that the angle of inclination is 30 degrees. Right? It's 30 degrees. You need to be able to dissociate this force into its component. Suppose the magnitude of this force is 20 newtons. 20 newtons. Now you need to be able to tell me what is the horizontal component of the force and what is the vertical component of that force. Now, it's very easy. You guys are used to what we call SOHCAHTOA, right? Now, if I want the vertical component of the force, the vertical component of this force is acting in this direction. Suppose I'm pulling this with a rope and I'm applying a 20 Newton force in this direction. Certainly, I'm not pulling the rope this way. If I was pulling the rope this way, I was going to apply what we call a horizontal force. But because I'm applying my force this way, I need to treat it that way and obey it. Now, if I want the vertical component of the force, I'm going to this SOHCAHTOA. Now, the trig ratio which involves, you can see this is the hypotenuse. The trig ratio which involves hypotenuse and the opposite side, hypotenuse and the opposite side is called psi. Now, the vertical component, I'll say force vertical, I'll just denote it as that. It will be 20 Newton sine of 30. 20 Newton sine of, why am I using sine? I'm using sine because sine is the trig ratio which incorporates the vertical side with the hypotenuse. Then I'll get my answer there. If I want the horizontal component of the force, this. Now we can see that according to mathematics, this is the adjacent side, this is the hypotenuse. The trig ratio which incorporates the adjacent and the hypotenuse is what? Is cos. Now that's why I'm going to do what? I'm going to say 20 cos of 30. Can you please punch your calculator and give me the answer? According to Pythagoras theorem, the answers that we get here, must be lesser than that side. What's the answer for the vertical component? 10. 10 newtons. What's the answer for the horizontal component? 17,32 newtons. It makes sense. Right? We can see this is lesser than 20, this is lesser than 20. It obeys Pythagoras theorem. It means we're okay. Please note, force is a vector, but I'm only interested in the magnitude here. Now, let's move to work. Work. We say work is done to an object. Work is done to an object if I apply a force in that particular object and I cause that object to move a certain displacement. Work is done on an object if I apply a force on that object and I cause that object to move a certain displacement. Now, if I'm doing work in the horizontal direction, I claim that work is done if I apply a force and I cause the object, if I apply a force on an object and I cause an object to move a certain displacement. So I claim that it's F delta X. F delta X. Now I'm saying work is done if I apply a force on an object and that force causes an object to move a certain displacement, delta X. Now that is work. Now let's talk about disparities of work. Number one, force needs to be applied. Secondly, distance needs to be covered. A force, for work to be done, a force needs to be applied. You need a force. Secondly, you need that force to cause an object to move a certain displacement, delta X. That's why I have F delta X. I'll make a typical example. Suppose Lindy applies a force of 30 newtons, right? A force of 30 newtons to a box that is resting on a horizontal plane. So I have a box that is resting on the horizontal plane, right? Now, Lindy applies a force of 20 newtons in this direction. Now, the distance that is being traveled by the box is 3 meters. And the question is, calculate the work done. The work done in this case will be work is equals to 20 times 3, which is 60. Question is what? 60. What are the unit measurement? Work is the energy transferred. Therefore, its unit measurement are joules. Work is the energy transferred. Therefore, its unit of measurement are what? are joules. So it's going to be 60 joules. Remember, energy is a scalar quantity, so we don't need to specify any direction. So is work. If energy is a scalar, so is work, because I'm saying work is the energy transfer. So it means work is also a scalar. Now let's change the dimension here. Suppose we are saying that Lindiwe applied a force horizontal. This force is horizontal, right? Meaning the angle of inclination between the force and the power of acceleration is 0, right? Lindiwe just applied a force of 20 Newton, and then that force of 20 Newton caused an object to be displaced a distance of 3 meters in the x direction. Now let's move. Now suppose Lindiwe now, we change things. Lindiwe applies that force in this direction. Lindiwe applies that force in this direction. Right? You are told that that force is still 20 newtons. That force is still 20 newtons. Now, the angle of inclination, they say, suppose is 20 degrees. Now, question is, calculate the work that is being done by the force that is being applied by Lindiwe. Remember, we are dealing with x, is F delta x. Now, meaning, I'm interested in what? I'm interested in the horizontal component because the box is going to move in the horizontal direction. It's F delta x. Meaning, I'm only interested in what? In the horizontal component. Therefore, the question, can you take a guess? The trig ratio that's going to enter here. No, I must find the horizontal component of my force. I must find the horizontal component of my force. Therefore, my work, whatever my work, will be given by F delta x cos of theta. The reason why we have cos of theta here, because we are interested in what? We are interested in the horizontal component of the force, because the box is moving horizontally. Now, the force was 20, delta x is 3, cos of 20. What's the answer? What's the answer? 20 times 3, cos of 20.
That's 56,38.
56,38 joules. Do you guys understand? Suppose here, no, it's fine. Let me leave that one. In our first example, I said Lindiwe applied a force of 20 Newton. Now she applied this force of 20 Newton parallel to the box, parallel to the direction. Meaning the angle of inclination was 0. Cos of 0 is 1. So if we want to apply this equation to our first example, remember the first example was just a box, right? Lindiwe applied a force of 20 newtons, meaning the angle of inclination, Lindiwe applied that force horizontal to the direction of movement, right? Now, the angle of inclination was 0 there. You will realize that if you say work is equals to F delta x cos 0. Cos of 0 is 1. Cos of 0 is 1. So we are going to have F delta x times 1, which is similar to our formula that we used first. But now, always, for exam purposes, the equation that you're going to use for work will be this one. Please use this one. If there's no angle of inclination, it means we have to substitute 0 here. And cos of 0 is what? Is 1. Now let's move. What is power? Power. If I say you have power, I'll make a typical example. Suppose I have Lindiwe here and I have Sentu here, right? And I'm giving them a task. I'm saying both of you have to lift a box of 20 kg, right? A box of 20 kg. Lindiwe is going to be considered to have more power than Sentu if Lindiwe lifts that box quicker than Sentu. Both of them are going to lift that box of 20 kg. Both of them. It's not questionable. Both of them are going to lift that box of 20 kg. The one who has more power than the other is the one who will pick the box quicker. So if Lindiwe picks the box quicker than Sentu, then Lindiwe is possessing more power than Sentu. Do you guys understand? Now, what is power in this case? Power is the rate at which work is done. How do we denote it mathematically? We're going to say P is equals to work delta T. And what are the unit measurement of power? What are the unit measurement of power? Power, power, power. What are the unit measurement of power?
Joules.
No, it cannot be joules. Joules are, joules is where? I'm giving you a clue. That the unit measurement of power is equivalent to joules per second. Joules, no, joules per second.
Okay.
Why? Work is given by joules, time is given by second, but it's over time, so joules per second. But there's something in physical sciences that is equivalent to joules per second. What? The physical equivalence of this is what? So the unit measurement for power is what? Any other questions? Any other questions? Now let's proceed to types of energies. I have to indicate, and I'm indicating again, that the energies that we have in the universe are not limited to these three. But your scope of work requires me to only focus on this. Now I'm going to talk about potential energy. Potential energy. In fact, there are two kinds of potential energies, and I'll dissociate them. We have what we call potential energy. Potential energy. Potential energy is the energy that you have because of your position, because of what you are standing. Then you have what you call potential energy. Then you have what we call gravitational potential energy. Gravitational potential energy is the energy that you have because of your position above the Earth's surface. Why? Gravitational potential energy is as a result of gravity. Now, what is the difference between potential energy and gravitational potential energy? The difference between the two is I can have potential energy on the moon. I can have potential energy on the moon. I can have potential energy on Earth. Because potential energy does not depend on gravity. But gravitational potential energy depends on gravity. I can only have gravitational potential energy on the Earth's surface. I can only have gravitational potential energy where? On the Earth's surface. Do you guys understand? I cannot have gravitational potential energy on the moon. I cannot have gravitational potential energy on Mars. I can only have it on Earth's surface because gravity acts on Earth. And the potential energy that we are going to concentrate on is what? It's called the gravitational potential energy. And it's denoted by U. I need to rub here. I need to. Okay. It's denoted by U is mgh. Now you can see that I said gravitational potential energy is the energy that you have because of your position above the Earth's surface. Your position above the Earth's surface. Meaning it depends on what? On mass. Doesn't it ring the bell? Remember we said the magnitude of gravity depends on the mass. The higher the mass, the higher the force of gravity that is going to act on you. Now it depends on the mass. You still remember this gravitational acceleration constant. Do you still remember that? And then it depends on the height. I'll make a typical example. Suppose I make a claim right now. That I'm going to kill myself. And the question is, how are you going to kill yourself though? And I'm going to say, I'm going to fall. All of you are going to laugh at me. All of you are going to laugh at me. Then I repeat the same statement. Suppose I move here at the Institute of Applied Science and Commerce. I move 4 stories up. Then I make a claim that, hey, I'm going to kill myself. All of you are going to tremble. all of you are going to tremble. What's the reason behind that? I possess more gravitational potential energy now. It means I can kill myself now because of my high gravitational potential energy. Why? I'm exploiting something that is very important there, which is the height. The higher the height, the higher the height, the higher the gravitational potential energy you have. I'll repeat the example again. If I come to you and say, hey, I'm going to kill myself now, and the question says, how are you going to kill yourself? Then I'm going to say, I'm just going to fall. All of you are going to say, this one is crazy, or your joke is very brilliant. But if I repeat the very same statement, 5 stories, you're going to tremble to say a dog is really dying. Because if I fall above 5 stories there, I'm going to die. Why? I'm going to be killed by what? Gravitational potential energy. Do you guys understand?
Yes.
Now let's move. We have what you call kinetic energy. Kinetic energy. Kinetic energy is the energy that you have because of your motion. I'll make a typical example. Suppose you are walking. It's going to be easier for me to stop you. It's going to be easier to stop you because your kinetic energy is lesser than the kinetic energy of someone who's running. Have you seen the rugby players? Yes. Before they can make an attack, they make sure that their speed is high, so that it becomes difficult for the defender to resist them. Why? They're exploiting something that is very important, which is called kinetic energy. If someone is walking, it's easier to stop that particular someone. But if I'm running and I'm charging towards you, it's going to be very difficult for you to stop me because my kinetic energy is higher than someone who's just walking. Do you guys understand? And normally we denote it by EK, and we say EK is half mv squared. Do you guys understand?
Yes.
Now let's move. We are going to talk about mechanical energy. And mechanical energy is the sum of potential energy and kinetic energy. Wait a minute. See, Doc is talking Greek now. I said to you, if you cannot explain physical sciences to a 2-year-old, then certainly you don't understand physical sciences. Here I come, I'm saying to you, mechanical energy is the sum of kinetic energy and potential energy. You see, I'm giving you mathematical symbols. Question is, can you explain it to a 2-year-old? Now let's talk about this picture right now. Let's imagine somebody who's riding a bicycle, right? And let's look at the motor of a bicycle. Let's look at a motor of a bicycle. By motor of a bicycle, I'm talking about the pedals and that machine that is rolling like that, right? Now, as we are pedaling, the bicycle is a very brilliant example of mechanical energy. As we are pedaling, you are constantly changing potential energy. Because as you are pedaling down, you are exploiting what? You are exploiting the height above the Earth's surface. And because you are exploiting the height above the Earth's surface, you are generating what we call kinetic energy. Without exploiting the height above the Earth's surface as you pedal, you cannot cause the bicycle to move. Now, a bicycle is a clear example and a clear demonstration of what we call mechanical energy. Because in bicycle, you constantly turn potential energy into kinetic energy. And again, kinetic energy gets converted to what? To potential energy, like that. So that's a very typical example of mechanical energy. Can you picture mechanical energy right now? Can you picture? So you're exploiting the height above the Earth's surface. As you exploit the height above the Earth's surface, we're getting motion out of it. And we're getting kinetic energy because of that. So as I convert potential energy to kinetic energy, that conversion is called mechanical energy. The type of energy that is going to result is called mechanical energy. Now you can explain it to a 2-year-old. I'm very impressed. Now let's move. Let's talk about the principles and theorems. Let's talk about the principles and theorems. But before we talk about the principles and theorems, we have been given mathematical explanations for types of energies. May you please allow me to give a mathematical description of mechanical energy? I'm saying EMEC is the sum of potential energy plus kinetic energy. Potential energy is given by mgh. Kinetic energy is given by half mv squared. Now let's move. Let's talk about the principles and theorems. And the principle that I'm going to talk, the first principle that I'm going to talk about is the principle of conservation of mechanical energy. Remember, we spoke about something that is conserved earlier. And at least you understand now when we say something is conserved, what do we mean? Now, I'll wrap here. Now I'll state the principle. It says the mechanical energy, the total mechanical energy of a closed system remains constant. The mechanical energy of a closed system remains constant. What do you mean when you say the system is closed? There is no external force that is acting on that particular system. So the sum of mechanical energy of that closed system remains constant. Now, I'm claiming that mechanical energy of a closed system remains constant. Mechanical energy of a closed system remains constant. I'm saying EK plus U initial is equals to EK plus U final. Now let me be more precise. I'm saying half mv squared initial plus mgh is equals to half mv squared final plus mgh, but this is final, this is initial. That's my claim. Meaning, mechanical energy of a closed system remains constant. And the definition of a closed system is what? The definition of a closed system is there's no external force that is acting on that particular system. So, when you, in an exam situation and when you are asked to state it, you are going to say the mechanical energy of a closed system is constant. The mechanical energy of a closed system is constant. And attach this formula. It will suffice more marks. Now let's talk about the second principle. The principle of work energy theory. The principle of work energy theory. But before that, I would like to make some examples here. Okay.